Ketones and aldehydes can be prepared from alkenes, and one method involves the oxidative cleavage of vicinal diols. But because diols can be prepared from alkenes, the net result is oxidative cleavage of the alkene. For the first step, the alkene can be converted to the vicinal diol by carrying out a dihydroxylation. So one method is to use osmium tetroxide in the presence of peroxides, such as T-butyl peroxide, and the net result is that OH is added to both carbons of the alkene. This proceeds by syn dihydroxylation because if you focus on this intermediate, we can see that both oxygens are added to the same face of the alkene. And then once this osmium intermediate is formed, then the reaction with peroxides leads to this product. Another method to carry out syn dihydroxylation is to treat an alkene with potassium permanganate, but it's important that it is dilute and that the reaction is carried out at low temperature. Potassium permanganate also gives syn dihydroxylation, leading to the same products as what we see with osmium tetroxide. For the second part of the transformation, our vicinal diol can be cleaved to give aldehydes or ketones. Once we have the diol, this can undergo per-iodic acid cleavage. So treatment of the diol with HiO4 per-iodic acid leads to the breakage of this bond where each carbon that's connected to the oxygen becomes a carbonyl carbon. So the piece on the left is going to look like this, and the piece on the right looks like this. Now the idea of cutting a molecule in half to be able to make aldehydes and ketones goes against a lot of our emphasis about trying to make carbon-carbon bonds in order to build up larger and larger molecules with more complexity. Sometimes this can be used to help to analyze a compound, and in other cases, this can be used as part of a multi-step synthesis when you might be using a naturally occurring compound as your bulk starting material. In many cases, synthetic chemists will use naturally occurring sugars because they have a lot of the stereochemistry, but maybe they don't need the entire molecule. And so it's a way to take advantage of what Mother Nature has already done. Ketones and aldehydes can be prepared from alkenes by carrying out oxidative cleavage. One of the methods is to carry out an ozonolysis followed by a reduction. So with this alkene, for example, ozonolysis leads to the cleavage between the alkene carbons, where each of these alkene carbons becomes a carbonyl carbon. So from the left side, we form this aldehyde, and from the right side, we form this ketone. We can think about this reaction more generally, and let's say we have an alkene that's connected to two alkyl groups on the left side, a different alkyl group, and a hydrogen on the right side. So treatment with ozone, which requires an ozone generator, this is typically carried out at minus 78 degrees Celsius. It leads to the formation of an ozonide. That looks something like this. And then reduction using something like dimethyl sulfide completes the oxidative cleavage, leading to this ketone plus this aldehyde. And so again, cleavage between the alkene carbons, where this piece is converted to this ketone, and this piece is converted to this aldehyde. An alternative is to react this alkene with potassium permanganate, when an alkene is reacted with a dilute solution of potassium permanganate and the reaction is kept cold, then this will lead to dihydroxylation, and it will stop there. But instead, if this is carried out using concentrated potassium permanganate and the reaction is allowed to warm up, then this intermediate will cleave, and that is going to give this ketone and this aldehyde. But under the conditions of potassium permanganate, this aldehyde cannot be isolated because it will be further oxidized to give the carboxylic acid. So potassium permanganate is an alternative to ozonolysis, but it's important to remember the distinction that ozonolysis will lead to the formation of aldehydes and ketones, whereas potassium permanganate will lead to the formation of ketones, but instead of aldehydes, you will get a carboxylic acid. In Organic 1, we talked about a number of different reactions of alkenes, and one of them is the acid-catalyzed hydration of an alkene. So this is an electrophilic addition, and if we look at this example where we have 1-methylcyclopentene, the alkene is going to share its electrons with sulfuric acid, and that leads to the formation of the more stable carbocation. And then water will add, and then proton transfer will give us this product. In other words, acid-catalyzed hydration gives us Markovnikov addition of H and OH across the double bond. Similar to the reaction with alkenes, the reaction of an alkyne uses sulfuric acid, but in this case it is also catalyzed by a mercuric salt. In this case, hydrogen and OH add across the triple bond, and it is Markovnikov addition, which means this carbon is where the hydrogen will become connected, and this carbon is where the OH will become connected. This leads to the formation of an enol, where we have the alkene and one of the alkene carbons is directly connected to the alcohol. This is an enol. Under these acidic conditions, however, the enol is not isolated because this will tautomerize to give a ketone. So an enol and a ketone are tautomers, which means they are isomers that differ only in the location of a proton. So we can imagine that this oxygen can share its electrons with the carbon, allowing this alkene to share electrons with an acid, and that is going to lead to this intermediate, and then all we need is a base to grab off this proton, and that brings us to the ketone. In another example, we can carry out the hydration of this alkyne, and this carbon is the one that gets the OH, this carbon is the one that gets the H, leading to the formation of this enol, and then this carbon is the one that becomes the carbonyl, this carbon becomes the methyl group. So with a terminal alkyne, the hydration of alkynes using sulfuric acid and a mercury salt, that is going to lead to the formation of a methyl ketone. If you have an internal alkyne, then the H and the OH could add to either alkyne carbon, and so if it's not symmetric, you can get a mixture of products. Another reaction we saw in Organic 1 when we were talking about reactions of alkenes was the hydration of alkenes by hydroboration oxidation. And once again, this led to the addition of hydrogen and OH across the double bond, but hydroboration oxidation leads to the non-Markovnikov product. Using this example of 1-methyl cyclopentene, treatment with borane THF for the hydroboration, followed by treatment with hydrogen peroxide for the oxidation step, this gives us non-Markovnikov and syn addition of H and OH across the double bond. So the H and the OH could both add to the back face, but they can also both add to the front face, so you will get this compound and its enantiomer. But again, notice we are talking about non-Markovnikov addition. Well, there's a version of hydroboration oxidation that can be carried out on alkynes. Once again, hydrogen and OH are added across the double bond, leading to the enol, which then tautomerizes to the ketone or aldehyde. Rather than using BH3THF, typically dicyamylborane is used. So dicyamylborane is a di-secondary isoamyl borane. So it looks like this. So quite bulky. So treatment of an alkyne with dicyamylborane followed by hydrogen peroxide and hydroxide leads to the formation of the enol, but in this case it is the non-Markovnikov addition. The OH becomes connected to the less substituted carbon, and the hydrogen becomes connected to the more substituted carbon. The enol is not isolated as it will tautomerize to give the aldehyde. So this is the same compound that we used on the previous slide, and treatment with sulfuric acid and mercuric salt gave the methyl ketone, but treatment with the dicyamylborane followed by hydrogen peroxide and hydroxide is going to lead to the formation of the aldehyde. So we have a couple of methods that can be used to convert an alkyne to an aldehyde or ketone. If it's an internal alkyne, then addition can happen in either direction. If you are starting with a terminal alkyne, then sulfuric acid and mercury salt leads to the methyl ketone by Markovnikov addition, and dicyamylborane leads to the aldehyde by non-Markovnikov addition. We have seen examples of esters being converted to alcohols. Well, can esters be converted to aldehydes? Let's take a look. If we have methyl benzoate, for example, if we were to treat this with sodium borohydride, remember that we get no reaction. So sodium borohydride is not strong enough. If instead we use lithium aluminum hydride, so a stronger hydride reducing agent, this is going to reduce the ester, but unfortunately it reduces it all the way down to the alcohol. And we're also going to get some methanol. So using lithium aluminum hydride in an ester, that doesn't help us to get aldehydes or ketones. Sodium borohydride isn't strong enough to reduce. Lithium aluminum hydride is kind of too strong. So dibol presents a nice alternative. So dibol is diisobutyl aluminum hydride. So we have aluminum with a hydrogen, and then this is connected to two isobutyl groups. So isobutyl, 1, 2, 3, 4 carbons, and there's a methyl branch. So we have diisobutyl aluminum hydride. Reduction with the diisobutyl aluminum hydride, and this is usually kept very cold, this will give us an aldehyde. So the ester is not reduced all the way down to the alcohol, it stops at the aldehyde. In other words, this is a great way to make aldehydes. So how does this work? We have our ester and we have our diisobutyl aluminum hydride. And so this is a source of H-, and so the H- is going to act as a nucleophile and share its electrons with the carbon, pushing these electrons up onto the oxygen, and that's going to form a complex with the dibol species. But it stops here. And another equivalent of diball doesn't add. This species is stable until hydrolysis occurs. So when hydrolysis occurs, you can think about these electrons coming back here to reform the double bond, kicking out the OR as a leaving group, giving the aldehyde. So this is the hydride that came from the diisobutyl aluminum hydride, and this is the original part of the ester. And here's another example. We have an ethyl ester diball at minus 78 degrees Celsius, followed by an aqueous workup, is going to convert this ester to an aldehyde. Now we have another reaction with acid chlorides, and if we treat these with a Grignard reagent, this is going to behave similarly to what we've seen with esters. So the Grignard serves as a source of a nucleophilic R group. So this is going to share its electrons with the carbonyl carbon, pushing these electrons up, and then those electrons will come back down, kick out the chloride, and we get a ketone intermediate. But then a second equivalent of Grignard can add, pushing up these electrons, giving us the alkoxide, and then on aqueous acid workup, we get the alcohol, a tertiary alcohol, where two equivalents of the Grignard have added. Now, if we were to use an organolithium instead of a Grignard, the same thing is going to happen. We get two additions leading to the tertiary alcohol rather than a ketone. But as an alternative, there's another species that's kind of related to the organolithiums, but it also includes copper. So this is a lithium dialkyl cuprate, also called a Gilman reagent. Now, a lithium dialkyl cuprate, we can kind of think of it like a mild nucleophile. It actually proceeds by a different mechanism, but the net result is it acts like a mild nucleophile. So we can imagine that this is going to add, kick these electrons up, they're going to come back down, kick out the chlorine, and we end up with the ketone, and it stops there. So for example, if we have benzoyl chloride and we treat this with lithium diethyl cuprate, this will give us ethyl phenyl ketone. So this piece came from the acid chloride, and this piece came from the cuprate. Now, where does the cuprate come from? So if we have an organolithium species and we treat that with copper iodide, that leads to the formation of a lithium dialkyl cuprate. But where do we get the organolithium from? Remember, if we were to use 2Rx plus, well, actually 4 lithium, that is going to give us 2 organolithiums plus 2 equivalents of lithium halide salt. We don't really care about that. The important thing is that from an organohalide, we can make an organolithium, and then we can make a lithium dialkyl cuprate. So for example, if we take 1-chlorobutane and we treat it first with lithium and then with copper iodide, we are going to make this lithium dibutyl cuprate. And then if we react the cuprate with an acid chloride, this is the product we will get, where this piece comes from the acid chloride and this piece was added via the cuprate. So we see that acid chlorides treated with cuprates, this is a source of ketones.